Welcome to this explainer. Today, we're unpacking exactly how SpaceX's Starship is completely rewriting the rulebook for manned missions to Mars. For decades, the whole prospect of sending humans to the Red Planet has been totally stalled. It's been constrained by massive costs and, frankly, severe weight limits. But with the advent of extreme capacity vehicles, everything changes. We're going to be looking at two very different blueprints for our first human landing and discovering how raw mass might actually be the ultimate key to unlocking another world.
Okay, so here's our roadmap for today. 1. Starship changes the rules. 2. SpaceX's Leviathan mission. 3. The Martian water gamble. 4. The DRA-6 alternative. And 5. Exploration over settlement.
Section 1. Starship changes the rules, the paradigm shift. So for decades, the dream of a Mars mission has basically been crippled by the astronomical cost of launching heavy payloads. I mean, before we can even think about building a Martian city, we have to answer the absolute most terrifying and complex question in spaceflight. How do you safely get the crew back home? Fueling a massive rocket to escape a gravity well and return to Earth is a complete systems engineering nightmare, and it dictates the entire mission design. The traditional NASA approach, which we saw in legacy architectures like DRA-5, was always to minimize mass at all costs. You engineered the absolute lightest, most complex systems imaginable, because every single ounce shot into space cost a total fortune. But Starship shifts this paradigm completely. As outlined in the source astrophysics papers, we can now convert risk into mass. Because launch costs are dropping so drastically, we can actually afford to send heavier, simpler, and much more robust systems. We don't have to engineer miracles just to save a few pounds anymore. We can literally use brute force mass to buy safety. To put that into perspective, Starship boasts a staggering payload capacity of 100 metric tons to low Earth orbit. That is 4 to 10 times more than other launchers, and it completely changes the mathematical realities of our mission. Suddenly, what seemed impossible becomes, merely difficult. Section 2. SpaceX's Leviathan mission, the direct approach. This brings us to SpaceX's incredibly ambitious baseline plan, which experts in our sources often refer to as the Mars Leviathan architecture. Under this concept, a massive Starship launches from Earth, lands 12 crew members directly on Mars, and eventually flies that exact same massive ship directly back to low Earth orbit. There are no secondary ascent capsules, no complex orbital rendezvous. It's an elegant, really simple architecture on paper, but that simplicity comes with an astronomical hidden cost. Section 3. The Martian water gamble, the core problem. The Leviathan plan has a massive, glaring bottleneck, and it all revolves around fueling that direct return journey. There is a staggering difference in the math here. To fly a heavy Starship off the Martian surface, you need to produce a terrifying 1,200 metric tons of methane and oxygen using local Martian resources. Compare that to the mere 40 tons required in older concepts. Generating 1,200 tons of fuel on another planet is a staggering industrial undertaking for humanity's very first visit. To make all that fuel, you obviously need massive amounts of water. This forces SpaceX to abandon the sunny equator and land at freezing higher latitudes where subsurface ice is suspected to be. This means terrible solar power efficiency and punishing psychologically harsh winters for the crew. And honestly, here's a truly wild detail. Just to get these Leviathan Starships out of Earth orbit initially, it demands up to 72 heavy lift refueling launches. That is a massive logistical gamble before anyone even steps foot on the Red Planet. Section 4. The DRA-6 alternative, a safer blueprint. Fortunately, aerospace expert Donald Rapp proposes a much more pragmatic alternative in the journal Igman Research, known as the DRA-6 mission. So instead of launching a giant Starship from Mars, a crew of 6 uses a tiny 9-ton capsule to lift off and rendezvous with an Earth return vehicle waiting in Mars orbit. We still use Starship's massive cargo capability to get us to the surface, but we don't try to fly the whole building back home, right? This cuts our required ascent propellant from 1,200 tons all the way down to just 40. And here is where Starship's massive payload really pays off. Instead of mining unpredictable Martian ice to make those 40 tons of fuel, large-scale mass delivery allows us to simply bring hydrogen directly from Earth. We then chemically react that Earth hydrogen with the abundant Martian carbon dioxide using the well-proven Sabatier reaction. Just like that, we manufacture our return propellants without ever needing to dig a single hole in the Martian permafrost. It's brilliant. By bringing our own hydrogen, we are no longer chained to the icy northern latitudes in a desperate hunt for resources. This one change frees the mission completely, allowing us to land directly at the sunny, much warmer Martian equator. We gain massive solar energy advantages, thermal stability, and vastly safer terrain. Basically, it removes the biggest unknown, which is accessible Martian ice, from the critical path of keeping our crew alive.
Section 5. Exploration over settlement, the ultimate goal.
So where does this leave us on a realistic timeline? And what's the actual goal once we touch down? Well, while SpaceX aggressively pushes for manned landings as early as 2028, the source author remains highly skeptical. The sheer complexity of the baseline Leviathan plan, validating heavy lift refueling, landing a massive ship, and building an alien water mining plant, means we are likely decades away from that reality. Rapp's analysis suggests that treating the first mission as a sprawling colony starter kit is just biting off way more than we can chew. Instead, the Perspective article emphasizes shifting our focus entirely away from a permanent settlement where colonists just sort of sit around in the early days. Starship's massive delivery capability allows us to build a robust central planetary science hub. From a warm equatorial base, the crew could deploy and manage globally instrumented remote robotic assets. Thanks to relay satellites, astronauts could control these rovers instantly with zero time delay, conducting more extensive scientific exploration in a few months than we have in the last 50 years. We are standing on the precipice of a thrilling, mass-abundant era in spaceflight. Starship gives us the heavy lift capacity to rewrite the rules, but how we use it really matters. So the ultimate question is this: should humanity's first visit to Mars be a desperate struggle just to survive a harsh winter mining ice, or a strategic, safe mission designed to truly discover an entire alien world? It's a fascinating choice that will definitely define our future in the cosmos. Thank you so much for joining me on this explainer. Keep wondering and keep looking up.